A major component of the air conditioning system is the fan coil unit. The fan coil unit houses the fan and the heat exchange coil. For the purpose of this exercise, I've included the filter. We're going to consider the efficiency losses of a moderately soiled fan coil unit versus a clean fan coil unit. We're going to state that our air conditioning unit has a 200 Pascal pressure loss at 1,000 litres a second when clean. After 3 to 4 years of operation with many filter changes, we now have a partly restricted filter with an extra 20 Pascals and a moderately soiled coil with an extra 40 Pascals pressure drop. This gives our soiled fan coil unit 260 Pascals pressure loss. We're going to look at our fan laws to get a theoretical flow rate for the air. I've amended the fan laws to consider a fan with a constant speed. What does change is our pressure through the system. We can see here that a change in our static pressure relates to the square of the change in velocity, and also that our power changes with the cube of the change in the velocity. It should be noted that fan laws are a good approximation, and in reality, out in the field, the changes won't be exactly the same as per our calculations, but it gives us a good idea of the efficiency losses. Here we have our fan curve. This blue line here represents the relationship between our static pressure and the airflow at a constant RPM for the fan wheel. This point here at the top of the curve we call blocked tight, and this point here at the bottom of the curve we call wide open. At blocked tight, the end of the fan is covered so that no air flows. We have our maximum static pressure for the fan. At wide open, we have no pressure drop across the fan. It is wide open and free to flow, and we have our maximum airflow. This green curve is the system curve for our clean fan coil unit. Where our two curves intersect, we can see that our clean system has 200 Pascals at 1,000 litres a second airflow rate, and our motor has 0.48 kilowatts power consumption. In the red line, we've mapped out where our moderately soiled system intersects with the blue curve at 260 Pascals static pressure loss. We will need to figure out what our litres a second is and what our kilowatt rating for the motor is theoretically. So making an estimate for our new volume of airflow, we write the following. We relate the static pressure drop to the square of the volume, manipulate, and then we plug in our 200 Pascals for the clean unit, divided by 260 Pascals for the moderately soiled unit, get the square root of that, and multiply that by 1,000 litres a second for our clean system. That gives us 877 litres a second for our moderately soiled air conditioner. Relating power to the cube of the velocity, manipulating, and then plugging in our numbers, we get 0.71 kilowatts for the operation of our fan with the moderate soiling. The difference between the kilowatt power consumption of the fan on the soiled air conditioner versus the clean air conditioner, when multiplied out by 10 hours a day, 5 days a week, 52 weeks in a year, gives us 598 kilowatt hours per annum. If we consider this with a rate of 27.5 cents per kilowatt hour, the extra cost for running that fan will be $164.45 per year. We're now going to consider the sensible cooling of our fan coil unit, what its capacity is when it's clean and what its capacity is when it's moderately soiled. So, assuming that this system has 19 kilowatts total refrigeration at 1,000 litres a second, and it has 15 kilowatts sensible, the difference between the total and the sensible is an amount of the refrigeration effect is used to take moisture out of the air, okay, and that will be about 4 kilowatts, and that's latent heat. What's left is 15 kilowatts of sensible heat, and that sensible heat is the drop in temperature you can feel from the air going onto our cooling coil and coming off. We're going to use the heat energy equation, which states that our watts or kilowatts of heat is equal to the mass of our medium times its specific heat times the temperature difference. When considering the clean air conditioning unit, we have 1,000 litres a second. So we're going to plug this into our equation. We're going to use the density of moist air and generalise that as 1.184 kilograms per cubic metre. We're going to use the specific heat of moist air as 1.025 kilojoules kilogram Kelvin, and that only applies to the sensible heating. We're going to use an air on coil temperature of 26 degrees, 50% relative humidity, and we're going to use the coil split air on off temperature difference of 12.5 Kelvin or 12.5 degrees C. When we plug our numbers into the heat equation, we do in fact get 15 kilowatts sensible cooling. That's based on 1 cubic meter a second at the density for moist air, the specific heat of moist air, and a TD of 12.5 K. When we apply the litres a second for our moderately soiled coil, converted to cubic metres, we get 0.877 cubic metres times the density for moist air times specific heat of moist air, and in practice this number would change and we may have a larger actual split, but we've kept it simple by maintaining the same coil split. And we get 13 kilowatts sensible cooling just from reducing our airflow. When we compare these two results, we see that we get a 15% penalty or 15% reduction in the sensible cooling just from our reduced airflow. The refrigerant cycle goes like this. At this point here, we have liquid refrigerant that is 100% liquid. It is injected by the metering device into the indoor coil, and there is flash of gas, and we bring the temperature down. Next, the refrigerant moves through the indoor coil, where it exchanges heat energy with the air that is drawn through the coil by the fan. Between this point and this point, we have a latent heat process where the refrigerant changes state from a liquid to a vapour rather than changes its sensible temperature. At this point here, we have a pure vapour. This vapour goes out to the compressor where it gets lifted in pressure and temperature to this point. Next, the pure vapour refrigerant is passed through the outdoor coil where it exchanges heat energy with the outdoor air. Again, we have a latent process where we see a change in the state of the refrigerant rather than a change in its sensible heat. And when we get to this point here, we have a pure liquid refrigerant, pure condensed refrigerant. By placing our refrigerant diagram into a pressure empathy chart, we can read off the empathy, or heat energy, at different stages of the refrigerant process. In our pressure empathy diagram, the pressure increases along the vertical axis, and our empathy, heat energy, increases along the horizontal axis. Our temperature tracks through like so. For our clean air conditioner, the process in the indoor evaporator coil will follow the 7-degree line. With soiling of the indoor coil, there is a reduced amount of surface area available for exchanging heat with the air. There is also a reduced amount of airflow. This causes a lower pressure temperature in the indoor coil. For our moderately soiled air conditioner, our evaporator indoor coil will be following the 4-degree line. This lower pressure temperature will create a higher heat of compression. That is, the work the compressor does to lift the low pressure temperature refrigerant to a high pressure temperature state where we are going to condense and reject the heat. Note that all the lines and the spacing here is exaggerated just for demonstration purpose, and they'd all be tighter and a lot neater in practice. We read off our chart that we have 160 kilojoules per kilogram refrigerant effect between this point here and this point here, the process of the refrigerant inside our indoor coil. For our clean air conditioning system, the heat of compression between this point and this point represents 25 kilojoules per kilogram. For the soiled air conditioner, the heat of compression between this point and this point will represent 28 kilojoules per kilogram. Next, we use the numbers cited off our pressure empathy diagram to calculate the theoretical power by our compressor to lift from a low pressure temperature state to a high pressure temperature state. Knowing that our clean air conditioner has 19 kilowatts of refrigerant total, that is sensible and latent load, we divide that by 160 kilojoules per kilogram, the process from this point to this point. This gives us our mass flow rate required, which is 119 grams or 0.119 kilograms per second. We do the same for our soiled air conditioner. It has 18 kilowatts refrigerant effect total, latent and sensible, and we come up with 113 grams per kilogram per second mass flow rate. We then multiply the mass flow rate by the heat of compression. For our clean air conditioner, heat of compression from here to here was 25 kilojoules per kilogram. That gives us a total of 2.98 kilowatts power theoretical. For the soiled air conditioner, the same process, but this time with a high heat of compression, we get 3.15 kilowatts theoretical power. Theoretical power does not allow for mechanical losses in the compressor. Comparing the two processes for the soiled and the clean air conditioner, we see that we get a 6% penalty for operating with a lower evaporator indoor coil temperature and moderate soiling. A general rule of thumb for air conditioning is that 1 kilowatt of refrigerant effect equals 0.31 kilowatts of electric power input. When considering that our clean air conditioner produces 19 kilowatts total refrigerant effect, and multiplying that by our rule of thumb, we arrive at the power input for the air conditioner of 5.89 kilowatts electrical. Our moderately soiled air conditioner has a 15% penalty for sensible cooling. It has 6% penalty for its theoretical power, heat of compression of the refrigerant cycle. This adds up to a total efficiency loss of 21%, neglecting the fan losses we calculated first. Applying our 21% penalty, we get 7.13 kilowatts electrical input to produce the same 19 kilowatts refrigerant capacity of our clean air conditioning unit. Business or small commercial use, we expect our air conditioner to run for 2,600 hours per year. That is 10 hours a day times 5 days a week times 52 weeks. If we were to consider Sydney's average temperatures, we would assume that about 106 of those hours that the air conditioning runs, the ambient will be above 30 degrees Celsius and our air conditioner will run at 100% capacity. For the rest of the time, we'll generalise and we'll just say that our air conditioning unit runs at 25% capacity, heating and cooling. If we calculate our power input for the clean air conditioner by 106 hours 100% capacity and 2,494 hours at 25% capacity, we get a total of 4,297 kilowatts an hour per year. When we apply the 7.13 kilowatts electrical power input for our soiled air conditioner to achieve the same kilowatts of refrigerant for cooling, we get a total of 5,201 kilowatt hours per year input. When we consider the kilowatt hour difference between the soiled air conditioner and the clean air conditioner and apply a rate of 27.5 cents per kilowatt hour, we get a penalty of $248.60 for running the soiled air conditioner. When we add the $164 penalty for running the fan on the soiled air conditioner, we get a total penalty of $413. Though these calculations are theoretical and are based on a very simplified version of air conditioning, we can see that the payback period for cleaning of the indoor air conditioning unit would be less than 12 months based on this $413 annual penalty.